Hello. Today's lesson will be on ionic bonding. I'm going to go through all the reasons, setting these different elements up, in this case potassium meeting bromine, setting them up so that we can see why they would be set up for an ionic bond, a full transfer of an electron from a metal to a non-metal. Alright, so for this activity, I would grab two different colors. It's helpful to see, since we're talking about valence electrons, the part of an atom that determines chemical properties. It's good to see where they come from, which atom they came from, which atom they go to. So, potassium and bromine. So let's tackle potassium first. Potassium is on our periodic table over here on the left-hand side. And we said generally if you take this diagonal line down through here, everything to the left of that line are metals. Everything to the right of that line are non-metals. On that line, there's some weirdos called metalloids. And generally I'll try not to throw those in, or we'll have better ways of telling how they'll react. So potassium, metal. Potassium is atomic number 19, so 19 protons. I have no information about whether it's an ion, and for this we want to assume neutrality anyway, because they become ions. So at the moment, 19 electrons. Electron cloud, or electron configuration. So we got 1s2, 2s2, 2p6, 3s2, oh, sodium, 3s1, stop at 3s1, 1s2, 2s2, 2p6, and then one more electron gets us to 3s1. So it has only one valence electron. Highest quantum number is 3. There's a 3s, but no 3p. So there, I just take that superscript. I've got one valence electron. Sodium with a single valence electron. If sodium could get rid of that valence electron, you would have 8. Its quantum number 2 shell would be full, with a 2s and a 2p, so 2 plus 6. Well, it'd have 8 valence electrons. Sodium wants to get rid of its 1 valence electron to be full. Therefore, it's gonna lose electrons. And it wants to lose 1 electron to get rid of, to get to the valence of 8. Electronegativity. So the introduction for all my students to electronegativity, and that's on this chart down here. Potassium has an electronegativity of 0.8. 0.8. We'll come back to the significance of that later. Alright, let's set up the other one in our other color. Bromine. Bromine is way over here. It's a halogen. Bromine is a non-metal. Bromine is atomic number 35, so it's got 35 protons, and when neutral, it's got 35 electrons. Electron configuration, we got to read it all the way out to there. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. If it sounds like I'm going way too fast for the cloud, the electron configuration, step back a couple lectures or look at some resources online for how to remind yourself of how electron configuration goes. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. So Lewis dot requires electron knowledge of valence electrons. We go to the highest quantum number. We've got a 4s and a 4p as our highest quantum. So take the superscripts. 2 plus 5 is 7. Bromine has 7 valence electrons. Just one away. So close. Alright, octet rule says they want 8. So rather than sodium getting rid of, bromine just has to gain a single valence electron, and it gets there. Electronegativity for bromine. Bromine halogen category, so 2.8. Here's our highest electronegativity at the top of the halogens, and it gets less and less and less as you go down the table, down and to the left on the table. So bromine is pretty high, 2.8 out of a max of 4. Alright, this electronegativity is how badly, essentially, or how much affinity an atom has for an electron. 4 being the highest affinity, the highest ability to steal an electron. So potassium, very low ability to steal. Bromine, very high ability, given that 4 is the maximum. And really what we care about is the difference between the two. On a scale of 0, well, not even 0, 0.7 to 4, this is almost as low as we go. And this is quite high. So big difference, bromine will steal. So go ahead and we're going to show some work and then a final copy. So bromine, I'm going to transfer my Lewis dot diagram down to here. And sodium. Alright, well, bromine is going to steal. So it is going to take this electron from sodium and incorporate it right here into its octet. That leaves sodium with what will look like none. I'm going to leave it blank, but remember it's actually got the 8 that are underneath it. Alright, as sodium loses a negative electron, it becomes positive. As bromine gains a negative electron, it becomes negative. Alright, so transfer these down to a final working. Sodium lost a negative electron, it becomes positive by 1. Bromine gained a negative electron. Therefore, it becomes negative. Here's why I did the two different colors. You can see that bromine had its original 7, but now it's got an 8th valence electron, thanks to sodium. This was a nice 1-to-1 conversion. In this packet, they will get harder. They won't be just a has one extra, needs one extra. You'll have to mix and match them. So the final product is Na. There's only a single Na, so I don't need a subscript here. Subscript says how many of that atom are in the compound or chemical unit, formula unit. And Br, I only have one Br. Alright. We will come back and practice balancing. If you want to try to balance this now, if you have any memory of doing that before, go for it. For right now, I want you to just give me the product that's the result of your drawings. Okie dokie. That is all from my lesson. Continue on through the packet. We've got calcium meets fluorine. We've got calcium meets oxygen. Aluminum plus fluorine, and aluminum plus oxygen. Okie dokie. Good luck.